Let us now take a look at a very consequential question. Are the electrons in covalent bonds shared equally? That is the question. To illustrate what this question is asking us, let us take a look at HF gas, hydrogen fluoride gas. It only becomes an acid when you dissolve it in water, and then it will become hydrofluoric acid. But as a gas, hydrogen fluoride, let us try to represent the Lewis structure of each atom. Hydrogen is from group 1A, it will have 1 dot. Fluorine is from group 7A, it will have 7 valence electrons. And to form hydrogen fluoride gas, they will have to share electrons. Let us assume that they share these 2 electrons. This is then the question. Are these electrons shared equally? And the answer is no, they are not shared equally. Why are they not shared equally? Let us first take a look at how this molecule would look like. This is what it will look like. That is what it looks like, not this. So, why are the electrons closer to fluorine than to hydrogen? It is due to a phenomenon that is known as electronegativity. Electronegativity is a phenomenon where an atom pulls shared electrons closer to itself. This means that a highly electronegative element will be very greedy for electrons. If a highly electronegative element is sharing electrons with another atom, it will pull shared electrons closer to itself. This is then the next question. What is the consequence of one atom pulling shared electrons closer to itself? Let us first look at hydrogen in HF. Hydrogen contributed 1 electron to the 2 electrons being shared, but both electrons are now very far away from hydrogen. So as far as hydrogen is concerned, hydrogen is thinking that it has lost 1 electron, the 1 electron it contributed. In reality, it has not. It is just that the electron is very far away from hydrogen. So, to show that the electron that hydrogen donated is far away from hydrogen, we would place a partial positive charge on hydrogen. Remember, a full positive charge would mean that an electron has been lost. But in the case of hydrogen, it's a partial positive charge. In the case of fluorine, fluorine would be thinking, that sucker, I took 1 electron away from it. In reality, fluorine has not gained an electron. It has only pulled the two electrons closer to itself. So we are going to place a partial negative charge on fluorine. Remember, a full negative charge means that an atom has gained an electron, which means that in this molecule, the electron density is moving closer to the fluorine, while the hydrogen side seems to be suffering from some kind of electron deficiency. This is what is known as a dipole. Two poles. We now have partial positive and partial negative charges. And whenever a molecule is such that the electron density is on one side of the molecule, while the other side of the molecule is relatively deficient in electrons, that type of molecule is said to be polar, which means that hydrogen fluoride gas is polar. So, what does it mean when we say something is polar? Polarity is the uneven distribution of the electrons in a molecule. The next question then is this: what determines whether an atom will be highly electronegative or very lowly electronegative? To answer that question, let us take a look at the periodic table. Let us begin with group 7A. The elements in group 7A need just one more electron to be like the noble gases. And because they just need only one more electron, they will be very aggressive to get that one electron. And because of that, the elements in group 7A are the most electronegative elements in the periodic table because they need one electron very badly. Let us now go to group 6A. The elements in group 6A need two more electrons to be like the noble gases. For example, oxygen will need two electrons to be like neon. Sulfur will need two electrons to be like argon, and so on. They will be aggressive for electrons, but they will not be as aggressive as the group 7A elements. Group 5A elements will even have less aggression than group 6A elements. In a nutshell, as we move away from the noble gases, the aggression for electrons will reduce, which means that electronegativity will have a trend. It increases from left side of the periodic table to the right side. So electronegativity increases from left to right. That is another way of saying that if we have two elements, say for example calcium and chromium, calcium will be less electronegative than chromium, because chromium will be a little closer to the noble gases. Now, let us take a look at elements in the same group. Electronegativity will increase up a group. That is another way of saying that lithium is more electronegative than sodium. Sodium is more electronegative than potassium, and so on. And let us take a look at group 7A, the group of the most electronegative elements. Fluorine is the most electronegative element in this group because electronegativity increases up the group. Actually, fluorine is the most electronegative element in the periodic table. To quantify electronegativity, fluorine, the most electronegative element in the periodic table, is assigned an electronegativity value of 4.0. Now, if you look at this, you will see the trend. Electronegativity increases from left to right, and you will see that it increases up the group. Let us now take a look at the applications of electronegativity and polarity. Are the following molecules polar or nonpolar? Let us begin with carbon dioxide, CO2. Before you can answer this question, you first will need to draw the Lewis structure for the molecule. We have done this before. The Lewis structure for carbon dioxide is this. The next thing is you would need to draw it so that it would adopt its normal molecular geometry. Carbon dioxide is a linear molecule, and we have drawn it linearly. The next thing is to look at the electronegativity differences in all the bonds. Oxygen is more electronegative than carbon. This can easily be seen in the trends for electronegativity that we have seen earlier. You can see that oxygen is more electronegative than carbon, as you can see on this chart. Because oxygen is more electronegative, the 4 electrons being shared between oxygen and carbon, remember, a double bond means 4 electrons are being shared. Those 4 electrons will be closer to oxygen than they are to carbon. And this is also the same thing that will happen in the other direction. Now, let us try to answer the question. Is carbon dioxide a polar molecule? The answer is no. And I know you will be thinking, but we just said that oxygen is more electronegative than carbon. Yes, you are right if you think that we have some polarity in this molecule. Because oxygen is more electronegative than carbon, oxygen will be partially electron rich, carbon will be partially electron poor, and the same thing for the other oxygen. But remember the definition of polarity. Polarity is the uneven distribution of the electrons in a molecule. In carbon dioxide, both sides of carbon dioxide are equally rich. So although we have some uneven distributions within the molecule. The overall molecule will still be non-polar because one side of the molecule is not electron rich than the other side of the molecule, since in carbon dioxide both sides are equally rich. So CO2 is non-polar. Let us take a look at the second molecule here, water. Again, we will have to go through the process. We will need to draw the Lewis structure for H2O. And if you draw the Lewis structure and you draw it properly according to the molecular geometry, this is what you will get. So the next thing is, are the bonds polar or not? Oxygen is more electronegative than hydrogen. So the two electrons being shared between oxygen and hydrogen will be closer to oxygen. And the same thing on the other side. What that means is that oxygen is partially electron rich if we are considering only the shared electrons, and the hydrogen are partially electron poor. But there is one other thing we have not yet considered. Oxygen has lone pairs on it. So apart from being aggressive, pulling electron density away from the two hydrogen, oxygen has two electrons that it is not sharing with any atom, which means that in any way you look at this, the electron density will be moving in the direction of oxygen. And that means that this side of the molecule, the side that has oxygen, is very electron rich, while the side of the molecule that has hydrogen is electron deficient. This side is electron rich. And because one side of the molecule is richer in electrons than the other side, water is said to be polar. Water is a polar molecule. Let us now take a look at question C. To begin, we know we need to draw the Lewis structure for NH3. And if you do this correctly, this is what you should get as the Lewis structure for NH3. The next question then is this molecule polar or not? Let us examine the electronegativity between nitrogen and hydrogen. If you look at the chart, you will see that nitrogen is more electronegative than hydrogen, which means that the two electrons being shared between nitrogen and hydrogen will be closer to nitrogen in each case. But apart from that, nitrogen has a lone pair of electrons that it is not sharing with hydrogen, which means that in every possible way, the electron density is only moving in the direction of nitrogen, which also implies that the side of ammonia that contains nitrogen will be electron rich, while the side of ammonia that has the hydrogen will be electron deficient. And because of that, ammonia is said to be a polar molecule. Now, I want you to observe a very quick trend here. In water, we have some lone pairs on the central atom, and the molecule is polar. In ammonia, we also have a lone pair on the central nitrogen, and the molecule is polar. So, I need you to note this right now. Whenever you have a lone pair on the central atom, the molecule will be polar. Whenever the central atom has a lone pair, the molecule will be polar. Let us take a look at question D. The first thing is to draw the Lewis structure, and if you do that, you should get something that looks like this. That is the Lewis structure for CF4, carbon tetrafluoride. The next question then is this molecule polar or not? Let us examine the bonds. Fluorine is the most electronegative element in the periodic table. So, when carbon is sharing 2 electrons with fluorine, the 2 electrons will be closer to fluorine. However, that will also be the same in all the fluorine atoms. What this means is that all the fluorine atoms are equally electron rich. And this has a tetrahedral geometry. All the fluorine atoms are positioned exactly the same distance from each other. Also, note that there is no lone pair on the central atom. So, since no side of the molecule is richer than the other side, and we do not have any lone pair on the central atom, this overall molecule will be non-polar. So, CF4 will be non-polar, although it has 4 polar bonds, but the molecule itself will be non-polar. If you're thinking at this point that why should I care if a molecule is polar or not? That is actually a very good question, because if you know whether a molecule is polar or not, you can predict whether the molecule will be soluble in water or not. Also, you can predict many of its chemical reactions and how it will relate with other molecules. But for now, let us take a look at solubility. A very simple golden rule in the lab is that like dissolves like. What does it mean? It means that a polar molecule will dissolve any other polar molecule. But a polar molecule would not dissolve a non-polar. Likewise, nonpolar molecule will dissolve nonpolar molecule. Let us take a look at an example. Sodium chloride. As you most likely know by now, sodium chloride has charges. A full positive charge on sodium and a full negative charge on chlorine. And because of these charges, by default, sodium chloride and any ionic compound is polar. They have poles, positive pole and negative pole. Which means that if you put it in water, it will dissolve. So sodium chloride is polar, and that means it will dissolve in water. But remember, not all ionic compounds will be soluble in water. Go and look at my videos on solubility rules. Let us take a look at another example. CH4. CH4 is non-polar. If you draw the Lewis structure, you will get something that looks like this. And carbon-hydrogen bond is simply considered non-polar bond. And since there is no lone pair on the central atom, this entire molecule is non-polar. If you put methane gas, CH4, in water, it will not dissolve. That is also why oil does not mix with water, because oil cannot dissolve in water. Oil is non-polar, while water is polar. So they will not dissolve in each other, and that means they cannot mix with each other. So your knowledge of polarity can help you to predict the solubility of a compound.